So, we're doing math 35. I'd like to lead it off. We're still working in R7, R8. I think this is closer to R8. We're doing a lot of radical shit today. Holy radical, man. That term needs to come back. Let's see, square root of x squared. Let's think about what's going on, because we can easily just say that's x. The square root and the square cancel out. I could rewrite this as 2 and then a 1/2, and then multiplying. And I get x to the first power. But does this always equal x? The rules say it does. If I follow this math, it does. Is this always true? In fact, it's not, which is some bullshit. You're like, these are the rules. What do you mean it's not always fucking true? If x equals -5, then I have the square root of -5 squared is the square root of 25, which is 5, which is not x. So we make a fix for that. This happens when the n on bar, the root is an even root. When we have an even root, like n equals 2, 4, 6. The square root of n x to the n is actually just the absolute value of x, is how we say it. That should be an n out front. And that makes it tricky. It's the negative numbers that fuck things up. So, in general, the square root of n square root of x to the n equals absolute value of x if n is even, and it equals x if n is odd. That's the real, like, really what's going on with square roots when you got exponents like that. If it's a number, you always know right away what's happening with it. You can just run with it. But variables, you kind of have to follow this rule. And this works for all kinds of variables. Like if I do the square root of z to the 6th power, this is the square root of z cubed squared. So I get the absolute value of z cubed. And the cube can go on the outside too. But if it's something like the 7th root of t to the 7th power, I now have odd exponents and odd index. It's just t. And sometimes the absolute values aren't completely necessary, as we'll see in the next example. If I have the square root of 81 r to the 8th power, s to the 10th power, should I get my radical enough room? This is like r to the 4th power squared, and this is s to the 5th power squared. And 81 is 9 squared. So when I do it, it's technically the absolute value. My pants are itching. I wonder if there's, I don't know, it's driving me nuts. That's the actual result. And then we don't need the absolute value for everything there. What doesn't need to stay in the absolute value? What's gonna be positive no matter what? Nine is one of them. 9's positive, right? Anything to an even exponent is going to be positive too. So I actually pull out the r to the 4th. It's not wrong to leave it in, but it's not necessary. S to the 5th, though, does need to stay inside. Because like -1 to the 5th power is -1. And so I can't just take it out without it. -1 to the 4th power is +1, so I can pull that out. The absolute value is not helping it. Whether it's negative or positive, it doesn't matter what's going on with r, it's not going to be negative, so I can just pull it out.
Sorry, I just want to, because you only took out the 9r4. You can make like a little note or something.
I can make what?
Like no, like which one? An explanation. I mean, like right.
So
Because
r to the 4th power is always greater than or equal to 0, like I showed here.
Okay.
Something to the 5th, so it's the even exponents. If the exponent is even, the outcome is going to be greater than 0.
Okay.
Does that make sense? Does like,
yeah, it's a little bit confusing.
If you plug in a negative number, squaring a negative number makes it positive. And so like having any even number is just like a bunch of squared numbers multiplied together.
Oh yeah, no, never mind. I understand. Yeah.
You got it? Okay.
Yeah.
Yes, because like r to the 4th is r squared times r squared.
Yeah, you explaining
each of these is greater than 0. So the outcome is greater than 0. Yeah. Mm-hmm. Yes, you should at least start with the absolute value, like I did here. I got the black lines around it.
So that's not what we took out, right?
Well, the ends are what I started with in here, the 8 and the 10.
So
Actually, the n is this. It's the index part. If that's an odd number, you're good to go. If it's like cube root, you're good to go. So let's look at one with the cube root. Negative 27 is negative 3 cubed. And if I want to write x to the 6 as cubes, I have x cubed times x cubed. So it's like, or I could do the other way around. I've got x squared times x squared times x squared. This is like x squared cubed. So when the index matches, the index is the thing outside, it's the what root we're taking. When it matches the exponent and the exponent's odd, that value that's here just comes out. Negative 3 times x squared. So we're always looking at the elf on the shelf. The math term is the index. If it's even, we kind of want to do that absolute value rule. And then we can always check to see if it's necessary. If you leave it in the absolute value, it's not wrong. If it's an odd number out here, you're good to go. It just comes out and you don't need the absolute value. In fact, you don't want the absolute value if it's odd. This applies even if we have it looking weird. The square root of 3x minus 4 squared. Since we can't see the index outside, it's an invisible 2. And that means we're going to use absolute value signs if the thing inside matches it. So we got 2 and 2. This is the absolute value of 3x minus 4. The parentheses aren't necessary. I was putting them there just to show you that that's the same match of what came out. Let's look at some more fun rules with radicals. Oh, power, yeah. So if I have the nth root of a and I multiply by the nth root of b, I get the nth root of a times b. That's like a multiplication version. There is a division version, and it does the exact same thing you would think. N over n to the nth root of a divided by the nth root of b is the nth root of a over b. And the real mindfuck one that doesn't come up hardly ever. The nth root of the nth root of x equals the m times nth root of x. This last one comes from the idea that this is the nth root of x to the 1 over n. And that means this is x to the 1 over n to the 1 over m, which is the x root of 1 over m times n. And now you can pull it back out and make it a radical again. All of this shit works in the exponent as a fraction form. You guys ready for some examples?
Yeah.
Yes. Yes, we're-
Awesome. Let's look at the square root of 5 times the square root of 45. This becomes the square root of 5 times 45. And I don't need a calculator for this, even though you're grabbing a calculator for this. Because what's 45 if I break that down in terms of numbers from the times table? It's 5 times 9, right?
5
So I've got a square root of 5 squared times 9. Square root of 5 squared times the square root of 9. 5 times 3 is 15. The other alternative is actually multiplying it out, and you get 225. Most people don't know that that's the square root of that is 15 now. That's when you have to like pull out that fucking calculator and type shit in. And if you practice doing it with this stuff, this is assuming you're going on to like calculus and doing like some STEM field shit. Practicing doing this kind of stuff now will help you in the long run, like big picture, not just in this class, but like in all classes. Because there you will do factoring in other classes and stuff like that, and it's just faster. It really is faster if you just use your brain on some stuff. Despite what ChatGPT will tell you. All right, let's look at another one. I already used red right there. I just need a different color. The fifth root of n cubed times the fifth root of n to the 7th power. Sounds like there's an elephant down the hall. Right? So I can put these together. And if you do it faster than what I'm doing, please do. I'm making sure that I get everyone's on board. This is going to be n to the 3 plus 7 with our rules. So I have the 5th root of n to the 10th power. If you don't like working with the exponents, you can always pull out as many 5s as you can, or something that matches the index on the outside. And then see what you can pull out. This comes out as just an n, this comes out as just an n. So I've got n squared. And it comes out as just an n because my index on the outside matches the exponents there. We could take a look at one where it doesn't. Here I skipped a step I wrote above. But I hope you guys will get comfortable with when the base is the same, you can add the exponents. So I've got the cube root of x to the 10th power. One way to do this, if you like sticking with radicals, just keep taking 3 away from the 10 until you can't do it anymore. If I take 10 minus 3, I got 7. 7 minus 3 is 4. 4 minus 3 is 1. So I need 1 left over like that. The ones that match the radical or the index, I can just pull out. And so I'm going to have x cubed on the outside times the cube root of x. Another way of doing that, starting from here, I can use that thing where the 3 becomes the denominator and the power on the inside becomes the numerator. And 10 over 3 is just 3 1/3. Which is 3 plus 1/3. Which is x cubed times x to the 1/3, which is that. And once you're familiar with it, going from here to here doesn't take a lot. You don't need to write all the middle ground. Fuck, are they teaching down this hallway? I'm getting a little worried. I mean, zoology and shit. Is there acting out here?
Oh, no.
I know we got theater over at the Visalia campus. So we were having, this is just a quick distraction. The math teacher were having a fun chat about ChatGPT. And how like it's harder to cheat with it in a math class unless it's online, because it will show you how to solve everything online. But like in an English class where you're doing the essays and shit at home for the most part, it does a reasonable, pretty good essay. It may not, it'll pull from sites that you may say are questionable, it may like, But it does pretty good essays. It also does computer code. One, we even found out you can ask ChatGPT, write me up a lecture on how to explain the product rule and the quotient rule in calculus. And it fucking gives a good lecture.
Is it like AI or what?
It's AI. It pulls from everything off the web that it's ever looked at, and they keep just being in more websites and more websites to look at. And then it's fucking good, like someone did that. They prompted it for a lecture on a calculus cockpit. And it came out with a pretty good lecture. I was like, all you need now is like a holographic image of like Gal Gadot or, Chris Hemsworth. And you'll have people studying STEM all the time. You're like, Wonder Woman teaching you that shit? Hell yeah. That could get people to pay attention. Well, maybe not.
It'll distract them, actually.
But if it's a holographic one, maybe not. It's a little less than it's like the actual person. But maybe, I don't know. She is very distracting to me.
Call me in 50 years.
Right. All right, let's look at some more. Let me give you guys one to do. That is a square root. Try to clean that up. Generally, any answer with a decimal answer is wrong because you had to round and therefore it is no longer correct. So don't rely on the calculator excessively. Like, don't put in square root of 11 over 169 and tell me the decimal answer. That's not what I'm looking for. Which I'm guessing is around, let's see, 0.23 maybe? Now I'm kind of curious. What is the square root of 11 over 169? See if my estimation skills are up to par. .255, not quite close enough. I thought it was going to be below a quarter, and it's above a quarter. So one of the rules we had with the radicals when there was division is we could break it up. $11 doesn't simplify. The square root of 11 is a long, but the square root of 169 is 13. And that's it. I guess you could say 1 over 13 times the square root of 11. But that one's fine. You guys ready for some more? Was that fun? Are we having fun yet? If you need it longer, say so. Some rules of simplifying the radicals.
Oh, sorry. I don't want to.
Bring back.
Can you come back just a little bit because, like, yeah, my computer was crashing and I
Oh,
couldn't
yeah.
write it. Okay, I'm done. Thank you.
Okay, now it's already in my head, I gotta tell you. I am like 11 and a half months older than my brother. When I was like 10, my mom like got like a student set of encyclopedias for me. We weren't rich, but I like to learn a lot. And algebra is in the A section, and I found it pretty early. And so like what we're gonna be doing later today or on Wednesday, I started toiling around like the most basic of algebra, and I liked it at 10. So we found, I was cleaning my mom's house this weekend with my brother, and we found an envelope that was addressed to my brother from 1985 when he was 9 years old. It was in my mom's handwriting, and it was from the math council, which was also in my mom's handwriting. But it wasn't from like local, so I think she sent a self-addressed, self-stamped envelope, like to get help on like, my child isn't doing as well in mathematics as they should. And he's not bad at math, he wasn't at my level. So she writes to this math counselor and they're like, ask the teacher this and this and this, and we can always help for $40 a month. 1985, if you up $40 a month for inflation to what it is now, $108 or something like that a month. Who the fuck asked for that much? For like, there's no internet in 1985. You were gonna be mailing shit. You could like tutor someone over like a video or anything like that, nothing. So like it was just, but that's what came in the envelope. This thing addressed to my brother, it was in my mom's handwriting. And I just showed that to him like, oh, you got, he saw it, like, what the fuck? Like it was delivered to him. Like, why did she write his name on it rather than her own name on it? Like, unless she wanted him to see it. Oh, look, the math council said they can help you. We didn't remember any of it we don't remember the letter ever being talked about, but it was, the postage mark was on there. It had gone through the mail. Good times. All right. Radicals and simplifying radicals. Radicals are simplified when well, the first rule, the radicand, that's actually what's inside the exponent or the radical sign. Has no factors with exponents larger than the index. I'll give you the example of each good and one that meets it, one that doesn't, on each rule as we're going down the list. So if I have the square root of 10, this is really an invisible 2 outside is the index. This is 2 to the first power times 5 to the first power. These are the factors. And the exponent is less than the index. So this is a valid or simplified answer. One that is not is the square root of 18. The square root of 18 is the square root of 9 times 2. Or 3 squared times 2 to the first power. Maybe I should say larger or equal to. Now the 2 on the 3 matches the index out here, so it needs to come out. The square root of 9 is 3. All that's left over inside is the 2 to the first power. So that is the simplified form. This is the valid answer. Square root of 18 is not simplified. Number 2, any questions on that one? Does that one make sense? It's kind of like what we were doing along the way, so hopefully that makes sense. Step 2. There are no radicands in the denominator, or no radicals in the denominator. And rather than trying to spell denominator where I will consistently fuck it up, I'm going to say the bottom of the fraction. I know how to spell it. I just constantly get ahead of myself. Instead of saying denominator, it always says demonator. I don't know why. Right? God does.
Wouldn't it actually be like nominal in the denominator, you like annihilate things? I guess not. Maybe not.
It's not a demon annihilator. Like Terminator doesn't destroy
Right,
terms.
that's exactly what exactly what's well, exactly what it's not necessarily.
All right. Square root of 11 over 13. We just had one. That's valid. Radical on top, not bottom. One that is not ready is, let's go with square root of 8 over square root of 6. So we got two things we got to fix here. The square root of 8 is not simplified as it is. We also have the square root of 6 on bottom. How you do this is up to you. I think it's kind of helpful to do kind of both at the same time, or maybe start with what's on top. Square root of 8 is 2 cubed over square root of 6. And this means I can write this as 2 squared times 2. And that means a 2 comes out. I've got a 2 square root of 2 on top, square root of 6 on bottom. So far, that's the best we could do. How we clean up radicals in the denominator, we get rid of the denominator, is we multiply top and bottom by that same radical. The people that were here for the Math 335, Saw a sneak peek of this? Because the square root of 6 times the square root of 6 is just 6. So now I've got 2 times the square root of 2 times the square root. I'm gonna, instead of writing 6, I'm gonna write 2 times 3. On bottom, I just have a 6. This square root of 2 and this square root of 2 can go together and make another 2. So I had my first 2, which is already there. That popped out another 2. And I'm left with square root of 3 on top, 6 on bottom. And of course, 2 over 6 simplifies it, or 4 over 6 simplifies to 2 over 3. And we got the square root of 3 on top. So this was 4 over 6, and I reduced it to make it 2 over 3. Now the radical is not in the denominator, and there's no factor inside the radical that can be simplified. This is a little weird, but next one I'll show you. Is there any questions on that one? Anyone need it up? I see writing. What am I teaching tonight in stats? All right. Rule number 3. The index on the radical and the exponent inside factors inside have no common factors themselves. I think the wording of that is a little confusing. I think when you see it, you're gonna be like, oh, okay. The cube root of x squared is valid. The 2 and 3 have no common factors. The ninth root of x to the 6 is not ready. Or simplified. This is kind of where you have to use the fractions as an exponent. This is x to the 6 over 9. And 6 over 9 simplifies to 2/3. And now I can put that back in the radical cube root of x squared. These two are identical in value, but the first one's not simplified, the second one is. Any questions on that one? This one is kind of stupid. All operations have been performed. We had an example of this just a second ago. We started with the square root of 8 over the square root of 6. Using all the radical rules so far, we got that down to 4 times the square root of 3 over 6. That was using all the radical rules. Now, all operations have been performed means you just got to simplify that more. Simplify further. Give you some examples to do. So the rules on all of these are simplify. Simplify the square root of 125. Not 125, 175. I do 175. Simplify -8 times the cube root of 125. And finally, simplify cube root of 128, a to the 6th power, b to the 8th power, c to the 10th power. I'll give you some good practice. Go ahead and take a few minutes and then we'll do them together. See what you can come up with.
Alexa, 128, raíz cuadrada tercero.
Lo siento.
Oh, sweet, you have your mic on.
Oh, I'm sorry about that.
It's a hot mic. This was over here ordering fucking dinner. He's some Mexican food. Chili relleno. A bit of refried beans. Someone told me something new to add to the Chipotle protocol. Bacon and Brussels sprouts broiled together.
Holy shit.
Have a little onion and garlic in there that, you know, it'll taste good. But then you got that Brussels sprout power. Boom. Yes, I was discussing the Chipotle protocol and looking for tips on how to make it better. That's how I roll.
Like Indian.
That's some of it. A lot of spices in it.
So I always order mine like a one spice. Feel if I'm feeling like bold.
A lot of this stuff is just like, it seems like. You can't taste anything but the spices. Like I'm like. What is in this dish other than, you know,
Curry.
curry, yeah.
You know, it's like, it's- It's,
Oh, I know what you're talking about. It's right behind Dunkin' Donuts.
Yeah.
Oh, yeah.
I got it one time.
It's all right for like a once in a while kind of thing.
$1.
Yeah, so not, yeah.
I mean, it's Valentine's Day, you gotta get a heart shaping.
Right. I might need to do that. Well, tell my wife we're ordering fucking pizza.
Happy birthday. No, order it and take it to her heart-shaped pizza.
If I do that, she'll have dinner made by the time I get there. I can't surprise her on Valentine's Day with that, when she's already told me what she's cooking. And it's not like she's whipping up some grand meal, it's, you know, like, a freezer bag thing, like it's called Voila dishes. They're actually pretty good, but they're like literally no work. You throw it in a pan and cook it, and we make some rice to go with it. They're pretty tasty. When she wants to be less productive. All right, everyone done? What'd you guys get for square root of 175? What's the answer there?
I got negative 40.
That's the next one. The next one you should have gotten negative 40. What about the one before it? 5 times the square root of 7. Anyone else get that? That's what I got too, because that's 175 is 7 times 25. Cube root of 125 is just 5, so this one was pretty straightforward. What about this one? Oh, I don't know what goes into it. So let's see. I know this is 4 times 32, which is 4 times 8. And this is 4 times 2. Look at that. So I'm going to rewrite that as 4 cubed times 2. I got lucky on that. This 8 to the 6th power is a squared to the third power. What can I do with the b's? I've got b to the third power times b to the third power times b squared. Maybe I'll just write it like that. Maybe I should have done that with the a's. Let's do that with the a's. I got 4 cubed times 2. The a's, I'm going to keep tearing apart the 6 by pulling out factors of 3. A cubed times a cubed, and we're out. 6 minus 3 is 0. I can do that with b. I did that here. 8 minus 3 is 5. Minus another 3 is 2. And I can't subtract 3 from 2, so I just stop with the 2. C, I can go from 10 to 7 to 4 to 1. So the 10 going to a 7 is c cubed. The 7 going to a 4 is c cubed. The 4 going to a 1 is c cubed. And then I'm just left with a c to the first power. Oh, don't forget the index on the outside, Mr. Jones. Because that's what we're matching to. That can be pulled out, that can be pulled out, that can be pulled out. Anything with a 3 as an exponent can get pulled out.
Well, it's the last year.
It's just a 1. And what's left on the inside is I've got a 2, and I've got a b squared, and I've got a c. So to clean that all up, I've got 4 a squared, b squared, c cubed times the cube root of 2b squared c. You guys ready for more? Next rule that we're going to use. I'll write it on this page and we'll work with it some more on the next. If radicands are like, which means they're the same. They can be combined through addition and subtraction. Some simple versions of this is 5 square root of 3 plus 2 square root of 3 is 7 square root of 3. So in terms of the radical part, just treat it like a variable. Treat this like you would do, like if this said 5x plus 2x, you can just add them together and have 7x. It works the same way with radicals that have the same interior part. Same with subtraction. 5√3 minus 2√3 is 3√3. Sometimes we might have to do a little work before we get to that step. You guys ready to do some work? Square root of 75 AB cubed minus B times the square root of 12 AB. So the insides don't look the same, so I can't do anything with them yet. But maybe if I clean them up, I can. $75 is 3 times 25. And I can rewrite the B cubed as B squared times B. Which means I can take the 25 out because it's got a perfect square root. And I can take the B squared out, is going to give me 5B on the outside. On the inside, what I have left is 3AB. On the second set, 12 is 4 times 3. So it looks like I can pull out the 4. The square root of 4 is 2. It gets multiplied by the B already outside. And I have 3AB. And now my radicands are the same. This becomes 5B minus 2B times the square root of 3AB, which is just 3B square root of 3AB. That's loud. I don't know what they're doing. And they're dragging desks repeatedly across the floor. Like fucking quit assembling your room already. So the reason why I did this is because that's kind of like what's going on along the whole way. I could have like a square root of 2 plus b square root of 2. As long as the square roots of 2's match, I'm effectively factoring out the square root of 2. And I get a square root of 2 times whatever's left over. And with radicals, it's just convention to put whatever's multiplying a radical in front. Simplifying some more, let's simplify. The 12th root of 2 to the 4th power. Well, the exponent on the inside isn't bigger than the exponent on the index on the outside, so I can't pull anything out. But 4 is a factor of 12. So I can rewrite this as 2 to the 4th power over the 12th. And that number reduces. 4 over 12 is 1/3. And this just ends up being the cube root of 2. Another crappy one that I don't know that occurs very often in real life. The 6th root of the 3rd root of 4 squared. So I don't know if it's easier to use the rules here or just like start turning the radicals into fractional exponents. I had 4 squared. And that's raised in this radical right here would be to the 1/3 power. But I'm still inside the 6th root right there. So I could do the 6th root also. I could have 4 squared raised to the 1/3 power, raised to the 1/6 power. And when we have exponents outside like that, we multiply exponents. And this is 2 over 18, which is 1 over 9. So this is really the 9th root of 4. Ready for more? Just getting a blood clot in my legs a little bit. Last set of rules, multiplying and dividing radicals. in weird ways. We already did basic multiplying and dividing. But you'll see what it. Let's just start out the gate with an example. Square root of 11 plus square root of 17. And I'm going to multiply that by the square root of 11 minus the square root of 17. Does this look like something similar? If I didn't have the radicals in there? This is a little like a plus b times a minus b. Anyone remember what that equals? Anybody? Oh, you guys are gonna have.
The A squared plus or minus B squared. Right? No. I put it up and then-
You're thinking Pythagorean formula, but you were close. It's a squared minus b squared.
I was gonna say that.
How many of you were gonna say that? I'm giving you shit, sorry.
I was like, I swear.
Well, then say it. Don't let me sit here and wait. Leave me hanging. So, how does that apply here? A is the 11 square root of 11, so I've got square root of 11 squared minus square root of 17 squared. We got 11 minus 17 is negative 6. These are called conjugates. It's when you have the same values in the front and in the back, but the sign changes between them. And when we do it with radicals, the answer doesn't have radicals. That's pretty fucking cool. It's only when the values are the same now. It's got to be the a plus b and a minus b setup. And it's got to be square root. That doesn't work for this shit. Let's take a look at another. Five plus the square root of 32 times 3 minus the square root of 2. I recommend simplifying it before anything that's got a weird radical beforehand. 32 is 16 times 2. So I can rewrite that as 5 plus 4 root 2 times 3 minus square root of 2. There really is no magic formula or pill or anything you can take for this. You just got to multiply it out. So we're going to do that. I'm gonna take the 5 and I'll multiply by the 3 and I get 15. And then I'll do the outside. 5 times negative root 2 is negative 5 root 2. The 5 doesn't go inside the radical because it's not inside the radical already. Then we'll start distributing the 4 root 2. 4 root 2 times 3 is, we do the 4 times 3 is 12. The root 2 doesn't have anything touching it. Finally, we do the last one. We've got 4 root 2 times negative root 2. This is like a negative 1 out front, so I can say negative 4. And then I multiply the radicals together. Radical 2 times radical 2. I'm actually going to write it in as radical 4 just for a moment. It will simplify. We know that square root of 4 is 2. But just to show you what's actually happening in case it doesn't simplify. So this becomes 2 times 4 right there. This entire thing is negative 8. Now we just got to start putting stuff together. We can add numbers that have no radicals together just fine. I can do the 15 and the negative 8 just fine, and I get 7. Now, when we're combining radicals, we got to make sure that the inside of the radical is the same. And in this case, it is. So we can combine those together. I've got negative 5 and 12 is plus 7. And that's as clean as it gets. Ready for more? All right, page turn. So we got division. We talked about it earlier. Like if I've got 2 divided by the square root of 7, we don't want to have radicals in the denominator. So how did we fix this last time? I multiply by the same radical, right? I'm going to do it on top and bottom. What about this? Cube root of 4/9. I'm going to rewrite that. First off, we're going to separate the cube root and put it on top and bottom separately. And now, before I show you that next step, I'm going to kind of show you the top way of looking at this 2 over root 7. This is the same thing as 2/7⁻². And we ended up multiplying by 7⁻² over 7⁻². And we ended up with 2√7 over 7⁻². Something similar is going to happen here. First off, we want to, if we can factor those things, we want to factor them. And maybe write them as exponents. So the 4 is 2 squared. And that's to the 1/3 power. And 9 is 3 squared. And that's to the 1/3 power. So the top, if I multiply that, I've got 2 times, or 2 to the 2/3 over 3 to the 2/3. What did I do here with the square root of 7 such that I ended up with a 7? In terms of exponents, not radicals. If I look at this, what did I do to end up with 7? I multiplied it by an the same base where the exponents add to 1. I want to do that here. I want to multiply this with 3 to some exponent. Where my exponent here, this is the 2/3. I want to add something to it such that I end up with 1. What do I got to add to 2/3 to end up with 1/3? Oh, I just ruined that. Start with 2/3 to end up with 1. I need to add 1/3 to it. That will be the exponent I use. Because multiplying by the cube root of 9 again isn't going to help us. We're not making any progress. But if I multiply by 3 to the 1/3, now the bottom is 3 3/3 like that, which is just 3 to the first power. The top doesn't really get any better. So I'm just going to go back to the radical. I had cube root of 4 and I have cube root of 3. So I can put those together and I get cube root of 12 over 3. Ready for more? Yeah. Cube root of 4 is the what we started with for the top, the 2 to the 2/3. I took the 2 to the 2/3 here and treated that as cube root of 2 squared. So the bottom of the fraction is the index, and the top of the fraction is the exponent on the inside. All right, let's up our game. We're going to do the cube root of a to the 5th power b divided by the cube root of a squared b to the 5th power. What we want to start off doing is make it one radical. And depending on how you like doing it, we can do this as a to the fifth power minus the 2, doing the division, and b to the 1 minus 5. We're going to end up with a cubed and b to the negative 4, which is going to be a cubed over b to the 4th. Or if you like writing them out and just canceling things that show up on top and bottom, you can do that. I think that's more work. If we do the subtraction with the exponents, we end up with a cubed on top, b to the 4th on bottom. And now we can separate it back out. We've got the cube root of a cubed on top, the cube root of b to the 4th on bottom. Cube root of a cubed is 8. And the bottom, I could do this as b cubed times b. And pull out what the b cubed as a b. And we're left with the cube root of b. So I've got a over b. And then I've got, instead of cube root of b, I'm going to write that as b to the 1/3. Because I don't want to leave any radicals in the denominator. Which means I need to multiply this on top and bottom by some version of b. I just need to figure out what exponent do I got to put here so that it equals 1 when I add it to the current exponent on bottom. 2/3. So I'm going to have a, and then this doesn't do anything. I'm going to shift it to the radical form. The radical form is the 3 is the index, and I've got b squared. Now, I already had one b, and now I've got another b. I have a b squared on bottom. You guys ready for the omega, the grand finale? This is called, and it's what we've been doing is called this along the way. Anytime we get rid of the radical sign in the denominator, it's called rationalizing the denominator. It clears the radicals on bottom. Now we've been doing that, but now we are going to up our game. I've got 2 over 3 plus the square root of 5. And that plus sign fucks things up. If I multiply by the square root of 5, the square root of 5 will help this one. But then I get a square root of 5 stuck on this one. So that doesn't help. There's one thing that gets rid of radicals in this situation. And we saw it with the very first thing we did in this little multiplying section. You use the conjugate. So you take the same thing and you just change the sign in the middle.
I think this is actually the right message to ask, like, why, about the negatives, and why, that's what I'm having trouble understanding, I guess.
Why we do it, or
Yes.
let's just see what happens with 3 plus square root of 5 times 3 times minus square root of 5. If you don't remember the a plus b and a minus b, what happens if I multiply this out? I've got 3 times 3 is 9. So we'll do FOIL. The good old FOIL, first, outside, inside, last. I've got 3 times 3 is 9. 3 times negative root 5 is
Never
negative.
mind, I see it now.
No, it's fine. If you have a question, others might have it. So it's worth talk about. Then we do inside plus 3 square root of 5. And finally, I've got square root of 5 times negative square root of 5 is negative square root of 25. These cancel out, don't they? And this is just 5. So I'm left with 9 minus 5 is just 4. I don't recommend you jump to that or doing it like that. I recommend treating it. I'll bring this down, what we started with down here. And we multiply by that. I recommend getting used to the a squared minus b squared. You are going to be tested on it. That will, I guarantee, the difference in squares will be on the test. Using that, we should have, this is a plus b, a minus b. I should have a squared minus b squared. Write that like that, 3 squared minus square root of 5 squared. On top, all you can do is distribute. But I'll do the distributing on the next line. So the bottom, we see that we get 3 squared is 9. Square root of 5 squared is 5. On the top, I'll distribute, and I've got 2 times 3 is 6. Minus 2 times square root of 5 is 2 square root of 5. And I'm left with 6 minus 2 square root of 5 over 4. This may not be that obvious, that stuff still simplifies. So I'm going to backpedal and teach you a better way of going about doing this. I'm going to leave that 2 factored out for now. And if I just deal with the bottom, I get the 9 minus 5 is 4. And now might be a little bit easier to see that something cancels. What simplifies here? 2/4 goes to 1/2, right? The 4 is 2 times 2. And I can cross off a 2 on top and bottom. So I'm going to be left with 3 minus the square root of 5 over 2. You can do that when you're here, but you kind of have to recognize all of these are even. So it's a little harder to recognize at that point. One more to kick it up a notch. We like kicking things up a notch, don't we? More power. Let's make it harder. Let's go with 3. What do I gotta do here? Correct. And it might help you if you put these in parentheses. Because the bottom is pretty easy to do. Following that pattern. On the top, I'm gonna have some more shit going on. I gotta distribute all that out. I've got 4 times 5 is 20. And 4 times root 3 is 4 root 3. Then I've got root 3 times 5 is 5 root 3. And root 3 times root 3 is root 3 squared. Which we know is 3, right? So we just start combining shit that's alike. We know 5 squared is 25. Square root of 3 squared is 3. That's 25 minus 3. 25 minus 3 is just 22 on bottom. On top, the 20 and the 3 here don't have any radicals, so I can add those together. 20 plus 3 is 23. And 4 root 3 plus 5 root 3, I'm adding up the numbers in front. 4 plus 5 is 9. At this point, I should check to see if it simplifies like the last problem did. 23 is a prime number though. And the other numbers are not factors of 23, so we're good to go. I think the next part, this is kind of like doing a simpler form, but I'm sure someone will fuck this up while doing the homework and not follow through what's going on. So I'm going to do the same problem where I just changed it. Like, I'll use a smaller number. Now we'll use the 4. I'm just going to use square root of 2 on top instead. And I'll keep the bottom as square root of 3. So when I multiply by the conjugate, fast forward to just saying the bottom's 22 because we just did that with the exact same things. There's no point in re-showing you that. That's not where, well, you might mess that up, but the top is probably one of the bigger spots. If I start distributing, I've got 4 times 5 is 20. And 4 times root 3 is 4 root 3. And then I distribute the square root of 2. I've got plus 5 square root of 2. And square root of 2 times square root of 3 is square root of 6. And someone is inevitably going to try to combine those. But that is the simplified form. none of the things on top combined. So it's an ugly answer, but it's the answer. That is one of the biggest things you can learn early in math. The answer doesn't have to be a nice little pretty number like 6. Oftentimes, the answer is shitty. Flat out shitty, just like life. Dark. Life doesn't have to be shitty. You gotta look for the silver linings. I didn't say we were done. No, get the fuck out. We're done. Just going around. Like, fuck you. I know it's 5 o'clock. You tell me I'm not done, but I'm done. That's it for today, folks. You too. Have a good Valentine's.